Today we will be looking at the properties of limits. As we begin looking at the properties of limits, I want you to remember that when we are looking at the limit of f at x, what this means is finding the limit of f at x as x approaches a. As f at a may not be defined, so we can only consider the behavior of f at x near x equals a. So we've been looking at this graphically, but now we're going to be looking at this through properties or laws to calculate the limits. It's really important that you guys look at all 8 laws here and you remember each of them as we are solving this. So to begin, we're going to first look at our first limit here. So number 1, the limit of k as x approaches a is just going to be equal to k because k is a constant number. So the limit of a constant is always equal to that constant. Where 2, the limit of x as x approaches a is going to be equal to a because the limit of x as x approaches a is equal to a. 3, the limit of f at x plus or minus g at x as x approaches a is equal to the limit of f at x as x approaches a plus or minus the limit of g at x as x approaches a. And this limit exists if it's positive or negative. So the limit of a sum and difference is the sum and difference of the limits themselves. 4, the limit of c times f at x as x approaches a is equal to c times the limit of f at x for any constant c. So c is just a number. So the limit of a constant times a function is the constant times the limit of the function. 5, as the limit of f at x times g at x as x approaches a is equal to the limit of both functions multiplied together. So the limit of a product is the product of the limits. The limit as f at x divided by g at x as x approaches a is the exact same thing as 5, except for the fact that we take the limit of f at x divided by the limit of g at x. Provided, however, that the limit of g at x is not going to be equal to 0, because we know if any time that something is equal to 0 in our denominator, that is going to make the whole function not exist. Number 7, the limit of f at x all to the power of n as x approaches a is equal to the limit of f at x as x approaches a all to the power of n for any rational number n. So the limit of a power is the power of the limit provided that the exponent is a rational number. 8, we can look at the limit as we take the nth root of f at x as x approaches a. Again, a previous law is very similar. However, we're now going to take the nth root of the whole limit of f at x. Okay, only if the root on the right side exists. So the limit of a root is the root of a limit provided that the root exists. Remember, I tell you this numerous times as we go through this unit, but please memorize and remember these laws. Okay, so putting a little star here, remember. So I hope that everybody does remember them as we go through them. Okay, so now what we're going to do is we're going to evaluate limits using our limit properties that we just discussed. So you may want to have your sheet in front of you as we're going through this so you're able to verify, look back and forth at those rules. And make sure that we always identify which property we're using. This will help us, again, remember these rules and properties of our limits. So our first one here, the limit of 5 as x approaches -1. This is just going to be equal to 5 because 5 is that constant term that we were discussing above. And this here is using property 1. Our next question here, number 2, we want to take the limit of x as x approaches negative 2. This here is just going to be equal to negative 2. Recall that the limit of x as x approaches a is always going to be equal to a. That comes from our property 2. The third one that we're going to look at is the limit of 3x to the power of 4 minus 5x as x approaches 2. Now we're going to use a couple different properties as we solve this limit here. So our first property that we're going to use, which I'm sure you can all see that, is going to be our property 3. As we take the limit of our 3x to the power of 4 as x approaches 2 minus the limit of 5x as x approaches 2. Okay, this is going to be our property 3. And we'll continue. And this here, 3 here, that number is a constant term. And so since it's a constant, by property 4, we can bring that 3 and multiply it by the limit of x to the power of 4 as x approaches 2. Minus, again, 5 here is a constant. So we can have minus 5 times the limit of x as x approaches 2. And this here, as I've said a couple times, comes from property 4. Our next part of this question here, we can take 3 times the limit of x as x approaches 2 all to the power of 4. Now that comes from our property 7. And we'll write that down. Property 7. And now we can go ahead and evaluate. So this here is part of our equation. The limit of x as x approaches 2. That comes from our property 2, as same as our example 2 here. So we have 3 times 2 to the power of 4 minus 5 times 2. Again, both of those come from property 2. And then we can just go ahead and evaluate here. So we will get this whole equation to be equal to 38 after we do our exponents and multiply. And so that's number 3. Number 4 here, we're going to look at the limit of 6x as x approaches 4. So by property 4 again, we're going to have 6 times our limit of x as x approaches 4. So that is going to be done by property 4 as we discussed, which is going to just be equal to 6 times 4, which comes from property 2. And we get an answer then of 24. So let's move on. Now we'll look at number 5. We're going to look at the limit of x minus 3 times 5x squared plus 2 as x approaches 0. So our first step here is we know by property 5 when we're multiplying two things together we can take the limit of each of those. So that's going to be equal to the limit of x minus 3 as x approaches 0 times the limit of 5x squared plus 2 as x approaches 0. Again, as I already had said, this is done by property 5. Next, we can actually use our property 3, and since we have this here to be x minus 3, we can separate that. So now we have the limit of x as x approaches 0 minus the limit of 3 as x approaches 0. Similarly, we can do that the same with our 5x squared plus 2. So this would be the limit of 5x squared as x approaches 0 plus the limit of 2 as x approaches 0. Okay, again, this was done using our property 3. So we're just going to leave our first part of our equation as is, and we're going to work with the second part. So in the second part, we can multiply 5 by the limit of x. I'm going to actually do two different properties in here, and we're going to square that all. Okay, so this is done both by property 4 and property 7, plus the limit of 2 as x approaches 0. So I just did two different properties to one part of our function here, our equation, and I'm hoping that we're all okay with that. If not, please ask tomorrow in class. And now we can just go ahead and evaluate using our properties from 1 and 2. So we have 0 minus 3 times 5 times 0 squared plus 2. Okay, again, this comes from our property 1 and 2. And now we can go ahead and just solve. So we get negative 3 times 2. So we get a final answer of negative 6. So now we'll continue looking at question 6 here. The limit of 5x divided by x minus 2 as x approaches 2. So by property 6, I know I can take the limit of both the numerator and the denominator. So that's what we're doing here. Okay, again, that was by property 6. So now we're going to use property 4 here, so 5 times the limit as x approaches 2 of x. So that's a property 4, and then in the denominator we're going to take the limit of x as x approaches 2 minus the limit of 2 as x approaches 2. And again, the top in the numerator we use property 4, and in the denominator we use property 3. And now we can go ahead and use property 2 for our numerator, and below we will use property 2 and 1. So this, I'm just going to continue above here, is going to be equal to 5 times 2 all over 2 minus 2. So again, that was property 2 and below property 1 and 2. And so now we can go ahead and evaluate. So this will be equal to 10 divided by 0. But anything, because it's divided by 0, what happens is that the function does not exist. So you'll get, when you put this in your calculator, you'll get an error. Now we're going to look at a couple of different strategies for evaluating limits. So our first strategy, the first one that we'll always try to do first off, is called direct substitution. And with direct substitution, exactly what the name says, all we're going to do is directly substitute our value in for our x. So we want to look at our first one, the limit of 3x squared plus 4x minus 1 as x approaches 2. So we're directly going to put that 2 in for our x. So this will be equal to x times 2 squared plus 4 times 2 minus 1. We can go ahead and solve this. We would use BEDMAS, obviously, do our exponents, and multiply and subtract and add, so we get 19. So I want you to always try this first, okay? So always try first, okay? It works for many cases, but again, always try this first. So for many functions, however, direct substitution works, but sometimes direct substitution can't be used. So looking at this limit here, the limit of x cubed plus 27 all over x plus 3 as x approaches negative 3. We can't use direct substitution here, because if we look at the numerator, if we just sub in negative 3 plus 3, that's going to be equal to 0. And when that happens, okay, that means that the function, the limit, won't exist. So always look at your different strategies that we're going to discuss when evaluating limits. So this, as I already said, we can't do because it doesn't exist, because the denominator is equal to 0. So when this happens, what this is called is it's an indeterminate form. So if the expression does not give enough information to determine the original limit, it is known as the indeterminate form. There are several types of indeterminate forms. So you can look right here. These are all our different types of indeterminate forms. So when we have 0 divided by 0, infinity divided by infinity, 0 divided by infinity, infinity divided by 0, 0 plus or minus 0, infinity plus or minus 0, and infinity plus or minus infinity. These are all different types of indeterminate forms. So we are going to look at some other strategies that we can use now to be able to solve this type of limit as we looked at above. So there are several strategies we can use to find equivalent functions that are the same as the original function for all values except at x equals a. So we're first going to look at our factoring strategy. So this is the exact same limit that we were discussing above. So we're going to look at factoring this one here. So to begin our factoring, we need to remember how to factor an x cubed. This is something that we did do in advanced functions, so you should be very familiar with this. If you aren't familiar with it, please go back and review those notes from advanced functions. So to factor this, we just have x plus 3 times x squared minus 3x plus 9. all divided by x plus 3. What you notice now is that we actually can go ahead and cancel those x plus 3's, giving us the limit of x squared minus 3x plus 9 as x approaches negative 3. So from this point on, we can actually now just substitute our negative 3 in for our x values. And what we get is 27. So we first factored, we cancel out our term in our denominator, one term in our numerator, and then we could use direct substitution there. So now we're going to look at rationalizing our strategy. So when we're looking at rationalizing, recall that from the very first day when we started to discuss rationalizing, something you did learn in grade 11 as well. So when we're rationalizing, remember we're rationalizing by the exact same term. However, if it's negative, you're going to have it as positive and vice versa. So we're going to go ahead and we're going to multiply both our numerator and our denominator by this root of x plus 16 plus 4. Now the reason that we need to rationalize this question here is because x is approaching 0. And since x is approaching 0, if we were just to directly substitute that x value in, we would have our denominator to be equal to 0, and therefore our whole equation, our whole limit, would not exist. So we're going to go ahead and continue here. So we're looking at our limit as x approaches 0, and when we multiply these together, we're going to have x plus 16 minus 16 all over x times the square root of x plus 16 plus 4. Notice here that we can actually cancel out those 16's now because 16 minus 16. So we would just be left with x in our numerator position, and then therefore our x's are going to cancel out. So what we'll be left with is just the limit of 1 over the square root of x plus 16 plus 4 as x approaches 0. And now we can substitute that x value in to our equation. So we're just going to have 1 over 0 plus 16 plus 4. When we evaluate, we're going to get 1/8. Now we're going to look at our fourth strategy here, which is one-sided limits. So when we're looking at this equation, we look at it and we say, can I put in our x value? So x is approaching 3 here. So if we put in x equals 3, we'd have our denominator to be equal to 0. And we know that doesn't work. We get our indeterminate form, and therefore we need to look at different strategies. So we then look 1 over x minus 3. What can I do with that equation? I can't factor it, I can't rationalize it, so how can I solve this equation? So what we're going to do is we're going to look at our one-sided limits. So what that means is we're going to look at the limit as it is approaches our 3 on our left side, and if it approaches our 3 on our right side. So we're first going to look at the limit of 1 over x minus 3 as x approaches 3 from our negative side. And when x is approaching 3 from the negative side, what that means is that it's approaching from the left side. So that's going to be actually equal to 1 over, we're going to take a number really close, just like we used to do in advanced functions. to 3. And that will actually be therefore approaching negative infinity. So let's look at the limit of 1 over x minus 3 as x approaches 3 from the positive side, so from the right side. So again, same as what we used to do in advanced functions, you're going to take your number really, really close to 3, so 3.001 minus 3. When we do that, we notice that it's approaching positive infinity. So since these functions, these limits are not equal to each other, this means that this limit therefore does not exist. Similarly, looking at our one-sided limits, we're going to look at b here, the limit of the root of 9 minus x squared as x approaches 3. If we just substituted 3 into our limit here, our function, we'd have 9 minus 3 squared. 3 squared is 9, so we'd end up just getting it to be equal to 0. So we want to look at, well, what happens on either side. So we're going to look at the limit of the root of 9 minus x squared as x approaches 3. First, this time we'll look at it as it approaches from the positive side. And when we look at this and it approaches from our positive side, we are just going to substitute a value in that's really close to our 3, but on the positive side of 3. So again, 3.0001 squared. And we're going to get that this here doesn't exist. So therefore, this doesn't exist at all, because it's going to be 9 minus a larger number, and we can never take the square root of a negative number. Okay, because anytime that we have a negative square root of any kind, we know that this can't be done. Okay, so however, we're going to look at the limit of 9 minus x squared as x approaches our 3 from our negative side. And when we do that, we're going to sub in a value that is really, really close to our 3. So 9 minus 2.999 squared. Okay, that's going to be really, really, really close to 9. So therefore, that's going to be equal to 0. Okay, it's getting really, really close to 0. These limits are not the same from the left side and the right side, so therefore, again, this does not exist. Okay, and our last strategy that we're going to look at is change of variable strategy. So when we look at this equation here, we look at every possible strategy that we can do. Direct substitution will get a denominator equal to 0. I don't know how to factor something that is to 1/3. So we're going to say, what can we do? Well, what we're going to do is use our change of variable strategy. So what I mean by change of variable strategy, what we want to do is we want to let u be equal to our x plus 8 to the power of 1/3. So that is now our u value. Well, we originally had x approaching 0, so now we need to know what is u going to be approaching. So u therefore is going to be approaching 2. Alright, so now we're going to substitute those values in, and also looking at our x, okay, x is going to be equal to u cubed minus 8. And the way that we get this is that we rearrange the above, where we have let u be equal to x plus 8 all to the power of 3. We're going to rearrange that, so you're going to take the cubed, you're going to cube both sides to get rid of the third. And then you're just going to bring the 8 over. And remember, anytime you cross the equal sign, it becomes negative. So now that we have what each of the values are going to be equal to, we can therefore now look at our limit of u minus 2 over u cubed minus 8 as u, not x, as u approaches 2. So used to saying x. So this is equal to the limit of u minus 2. Again, we're now going to factor in our denominator this time, our u cubed minus 8. And we get u minus 2 times u squared plus 2u plus 4 as, u approaches 2. So this is equal to the limit of, it's just going to actually equal 1 because our u minus 2's cancel out. So we have 1 over u squared plus 2u plus 4 as u approaches 2. We can then now just directly substitute our value of 2 in. Sorry, that shouldn't be squared there, it should just be 4. We should have 4 plus 4 plus 4, so we get 1 over 12. So the limit is going to be equal to 1 over 12. Now I want you guys now to go ahead and try B on your own.